starring Heather Martinez, Ashley Morrison, and Kaylee Slusser.
Hi, I'm Keely Slesser, and today we will be talking about how Newton's 3 laws of motion exist in the fabulous game of softball. We will be sliding, hitting, catching, and throwing. We will also be demonstrating ground balls.
Newton's second law states that net force is equal to mass times acceleration.
Newton's second law comes into play when throwing in softball. Ashley threw the softball and baseball with the same force, due to the difference in mass. The mass of a softball is 180.4 grams, while the mass of a baseball is 147.6 grams. The baseball will have a larger acceleration because it has a smaller mass.
Newton's first law states that objects will remain in the current state of motion unless acted upon by an outside force.
In the act of catching a softball, Newton's first law is demonstrated. If a player goes to catch the ball and misses, the ball will keep flying past the player. If in a different scenario, the player catches the ball with their glove, the glove is the outside force that stops the ball from flying.
The glove acts as the outside force that changes the current state of motion of the softball. Now we will move into hitting. Hitting is an excellent example of Newton's third law.
In act of hitting the ball, the bat applies a force to the ball. So, Newton's third law tells us that the ball also applies a force back on the bat. These forces are equal in magnitude, but in opposite directions as seen in the picture. As the ball moves towards catcher, the bat applies a force to the ball, causing it to slow down, and then speed up in the opposite direction. As the bat hits the ball applies a force to the bat, causing it to slow down.
Newton's second law states that net force equals mass times acceleration. To demonstrate this, we will examine a base runner sliding into a base.
How fast you are running is your initial velocity, which in Heather's case is 3.2 meters per second. How fast you are going when you get to the base is your final velocity, which is 0 meters per second. The time from the start of the slide until Heather reaches the base is 0.47 seconds. Using these values with the average acceleration, we calculated the magnitude of Heather's acceleration as she was sliding, which is 6.8 meters per second squared. Then, using Newton's second law of motion, net force equals mass times acceleration, we calculated the net force on Heather as she was sliding, which is 1.2 newtons. A ground ball is a perfect example of Newton's first law. Newton's first law states that objects will remain in the current state of motion unless acted upon by an outside force.
When Heather stops the ball with her glove, the glove is the outside force on the ball. When Heather misses, the glove does not apply a force to the ball, so it continues rolling. If Heather hits the ball, it will apply a force, changing the motion of the ball even if it does not stop the ball.
In this video, we've shown you 5 different ways that physics applies to softball, with each demonstration proving Newton's laws. The first law states that objects will remain in the current state of motion unless acted upon by an outside force.
We proved Newton's first law by demonstrating catching and stopping ground balls.
Newton's second law states that net force is equal to mass times acceleration.
We demonstrated Newton's second law by throwing a softball.
Lastly, we proved Newton's third law, which states that for every action there is an equal but opposite reaction when Kaylee hit the softball. Initial velocity, which in Heather's case,
Alright, Newton's first law states that objects will remain in the current state of motion.
Hurry! Hurry!
Well,
when the bat strikes the ball. When ball is traveling towards the batter.
in this video, we have shown you 5 different ways that physics applies.
We proved Newton's first laws by
Newton's first law states that objects will remain in the current state of motion. What?
I hit a softball. This shows that when the action of the ball moving,
Net force is equal to the mass times acceleration.